Hello, everyone, and welcome to the latest edition of our podcast interview series. As always, we want to make these sessions interesting and interactive. So please do introduce yourself, tell us where you're joining from and what you do. And of course, please feel free to add your questions to the conversation. And by the way, if we don't get to all your questions, other attendees are welcome to answer some of the questions as well. Now, today's interview, as you well know, is with Ryan Blue, who is co-creator of Apache Iceberg. But before we get to the actual interview, I have a few quick slides I want to review with you. So we've quite a number of upcoming events. And by the way, you can catch all of our podcasts at odsc.com podcasts. But please do subscribe on your favorite podcast app, iTunes, SoundCloud, Spotify. We do have a number of free webinars coming up as well. And I'm glad to say we're getting our in-person meetups running again. And we'll be doing, I think it's the 4th or 5th this year meetup. And this one will be in Davis Square in Cambridge, Massachusetts, if you're around the area. And ODSC East is coming live to Boston on April 23rd to 25th. That will be hybrid. So you can join us in person or virtually. Very pleased to say that Ryan will be joining us virtually for that conference, and we can speak a little bit more about that later. But there are free passes available, keynote passes, expo passes, and then we do have discounted training passes available as well. And next we have is, super excited to say we're co-hosting. This is our 2nd annual Data Engineering Summit. That's one track over 2 days. So we have some great sessions happening that as well. And do check out the schedule if you're curious about that or interested about data engineering. And then, of course, as just mentioned, check out our podcast. We generally release on Mondays. And hopefully this one will be released on Monday as well. All right, so on to our main event for today. Ryan, welcome to the podcast.
Hey, thanks for having me.
So I just want to give you a little background on Ryan. So Ryan, as you may know, has been a pivotal figure in the world of data engineering. He's co-creator of Apache Iceberg. And his remarkable journey has seen him make substantial contributions to data infrastructure at top companies like Netflix, Cloudera, and Ryan is now at Tabular, a company co-founded. And of course, he is either a PMC or primary committer to lots of Apache Software Foundation projects, including Apache Parquet, Apache Spark, Apache Avro, and of course, Apache Iceberg. And Ryan's work, we have to say, has really been instrumental in advancing the field of data engineering, not just for his leadership in developing Apache Iceberg, but has really helped transform data lakes into more structured and reliable data environments and influencing companies in how to scale their data in the cloud. So today with Ryan, we're going to do a deep dive into his insights, experience, and how, as it says in the title, open table formats are reshaping the data industry. So Ryan, really want to talk quite a bit about your background, your work at Netflix, Apache Iceberg, but just to ground our conversation here and give us an overview, can you tell us a little bit about, give us an overview rather of data warehouses, data lakes, and now the new kid on the block, which would be data lakehouses?
Oh yeah, no problem. So I guess it all began kind of with data warehouses, where we had, I guess, analytic workloads, and some very famous people came and said, hey, what if we started taking and putting all of our data in the same place, basically to be able to take advantage of all of the data sets that you want to pull in and correlate together. And of course, that was really large. So those databases were expensive and became distributed and were very expensive, hard to run, and things like that. And then Google famously came out with their GFS and MapReduce papers, and then that sort of sparked this Hadoop revolution, where people were building essentially hand-coded data tools using commodity hardware and things like that. And that sort of forked off of that database lineage and gave us what eventually evolved into the data lake. Only that was a whole bunch of distributed systems engineers like me. And we didn't exactly know what we were doing in the database world. And I would say didn't realize we were building databases until way, way too late.
Interesting.
Yeah. And then in the meantime, this idea of separating storage and compute and moving to cloud eventually led to, bigger MPP data warehouses and then cloud data warehouses and that sort of thing. And we sort of had these two worlds co-evolving. That's sort of where I came in. I was on the Hadoop side of the world and dealing with the sort of shaky foundations of the data lake space. And then I would say, to sort of tie that off with the, I guess, lakehouse idea. I'm not a huge fan of that term, but I think what most people mean, not vendors, what most people mean by lakehouse is basically a data lake type situation where you can use many different tools, but with the guarantees and sort of like SQL lineage of a data warehouse.
No, that's an excellent overview, Ryan. I do remember it took quite a few years for people to consolidate on what the definition of a data lake was. And data lake house is, from a marketing perspective, it's an excellent term. Who doesn't want a lake house, right? So let's get into want to talk about the creation story behind Apache Iceberg, because as I mentioned in the brief bio there, you were at Netflix, a great data engineering company, as I'm sure many people know. But during your work there, what were the primary challenges or limitations that you observed in existing data architectures while at Netflix that inspired you and your co-creator to create Apache Iceberg?
There were three sort of big areas. Number one was just correctness. When I alluded to a shaky foundation on the data lake side, it was pretty much crumbling. There was a pretty bad foundation, and that meant that we couldn't do we couldn't guarantee correctness. So things like if I want to rewrite a portion of my table, that was unsafe, and people might see that operation midway through, right? You might get dirty reads, you might get completely bogus results if you happen to be reading what I'm changing. And, as a data practitioner, I'm sure you can sympathize that that's a nightmare. So we built up human patterns to work around it. Like basically you don't maintain your data. You try and write it the first time, like the right way, but you don't ever change it because that's a risk. So we had just correctness issues everywhere. Those correctness issues caused performance problems. And performance problems were particularly bad for Netflix because we were in S3, so our latencies to storage were completely different. And we were, basically like operations could take longer. It was just a performance nightmare. And we were trying to build an internet scale, data analysis platform. And so we had scale challenges as well. But the big one that both of those two things feed into is, I think, the productivity of our data engineers. If you can't go and make something faster by rewriting the data and clustering and like running some tricks because, hey, you wrote it the wrong way the first time and we can't do anything about that. If the platform itself can't make those good decisions and go compact data if you accidentally wrote it the wrong way, if you've if you rename a column and get zombie data back from 2 years ago, like those are productivity issues. And so like the biggest thing was really these problems in our data lake foundation were causing, productivity nightmares with our analysis.
No, that's really fantastic insights, Ryan. And yeah, definitely want to get into some of those pain points. The Schema Evolution is one of my favorite, but let's talk about the open table format and what's so special about that open table format.
Yeah. So an open table format is basically solving the problem of how do we keep track of what's in a table? What data files make up a table? And it's really easy to understand the old model, the one that we replaced, which was like you just have a whole bunch of directories. Say I have a data set laid out by time. I have a whole bunch of directories, one per day, and whatever data files are in those directories, those are the data in my table. So you're solving this problem of what data files constitute the data in this table. The problem is if you're doing that and you're relying on directories and directory listing and things like that, you can't make, as I alluded to earlier, atomic changes. You can't, hide what you're doing from someone else. If you want to replace a day's worth of data, you have to go delete that day's worth of data and then stick new data in its place, or duplicate for some period of time and delete the old. And it does not work well. So what Iceberg did was it basically built a metadata system around keeping track of table metadata. What data files are in the table, what's in those data files, so that we can effectively go prune and not read any more data than we need. How do we keep track of schema and those sorts of concerns? And then I think pretty critically, we did that in a way that could be plugged into all of the various tools that we were using. So Pig, Hive, Spark, Trino, which was called Presto at the time. All of those tools could use it simultaneously without knowing about one another.
No, and it's interesting as well because, data engineering, we've been talking about data engineering quite a lot for the last 3 or 4 years now, but I think that whole data engineering itself has been around for quite a few decades, but I think it was really companies like Netflix and LinkedIn and Google that really put data engineering on the map. And then, of course, I guess back then you were a software engineer, but I can say data engineers like yourself put data engineering on the map, so to speak. And interesting what you say about working with those older formats, because for most of us working with Apache, Hadoop, and Hive, it worked fine, but we weren't scaling at the levels that companies like Netflix, Google, Amazon, and LinkedIn were. So, yeah, so that was great insight. But what I really love about that is the fact that it wasn't kept within the company, right? So in the open table format in particular, so I assume the open source is the open part of the open table format. And can you tell us a little bit about how has being open benefited the project?
Oh, it's been huge. I usually talk about how hard it is to have your own custom solution in this space. So we had something that was not as good as Iceberg because it was sort of hacky. It was built on top of the Hive table model. We called it the batch pattern. And the first couple tasks I had at Netflix when I started in 2016 were to port this to a new version of Spark. So take all this work that we've done and redo it on a new version of Spark. And that was something that we did over and over and over because the way that we were providing additional guarantees on top of the Hive table format was just really hard for us to maintain internally by ourselves. So part of this was just, I don't want to have to do that every single time. I just want a clean way to plug into Spark and something that I can reuse that gives me better guarantees. Opening up allows us to do that in Trino. At the time, we just said, don't write from Presto Trino because we haven't done the work to make it work, to provide the extra guarantees over there. So don't use it. That's not great. We want people to have, full access to the features of any of these compute platforms that they were using, whether that's, streaming like through Flink, the ad hoc Trino queries, ETL and Spark and Pig and whatever. Like, we really wanted all of that to work well. And to do that, you have to go to the open world, right? You have to make it something that's collaborative so that you get another organization saying, we really want to maintain this portion of it and extend it. I really love that about the open source community. People come up with great ideas and do new things, and it's all work that we would either never even think to do, or that we can just benefit from.
No, very well said. And I was just looking at GitHub and a few other sources this morning. Still a very, very active and large open source community. And I would encourage anyone who's looking to contribute to open source projects, please take a look at some of the ones Ryan is mentioning, because the help is always appreciated, not to mention the experience and you get from contributing to these projects. So, Ryan, you mentioned a couple of key points here about scalability, performance, architecture, and we did promise on the title of this live stream / podcast that we do a little bit of a deep dive into Apache Iceberg and open table formats, and you are definitely the person to do a deep dive on this. So just looking at the architecture first, can you give us more detail on the underlying architecture of the open table formats and Apache Iceberg, of course, and explain its advantages? And you already gave us a little insight into how it scales compared to traditional data storage solutions, but we'd love some more insights on that if you.
Yeah, absolutely. So like I said earlier, the fundamental problem that we're solving is how to keep track of what files are in a table. And then how do we make changes to those files, to that set of data files. And that's essentially where we began. We wanted to be able to make atomic changes. Well, keeping track of what files are there was a pretty easy next step. Well, let's keep track of files with data files, right? Let's have a metadata layer, and then break that metadata into multiple, what we call manifests, that track data files. Then you just have to have multiple manifests and keep track of which manifests make up a given version, or what we call a snapshot in Iceberg. And so we have a list of manifests that gives us this sort of 3-level structure: data files, manifests that track data files, and then a manifest list. Now, that might seem a little overcomplicated, but the reason for multiple manifests and thus the manifest list layer is that we don't want to be making large changes to table metadata, right? The analytic tables generally have a huge amount of data, and they're slow changing. So, you might add a new day's worth of data, but you're not changing the 1,000 other days in the table. So having multiple manifests allows us to change just very small portions of the table metadata at a time. And you get, several orders of magnitude reduction in the amount of data at every level in this, what is essentially a persistent tree. And that persistent tree also gives us the ability to basically index every level as you go down the tree. So data files, we keep track of column level statistics, how many nulls are in each column, min, max values. And then we keep track of ranges of those values in manifests at the manifest layer, at the manifest list layer, so that we can actually go very quickly for a given filter, figure out which metadata files do we need to read, which manifests of data files do we need to read, and then which data files do we need to read. And so it all sort of plays into a working system where you have both low write amplification, which is how much you have to change in a table's metadata in order to write new data or change it. as well as a really effective index structure at the same time.
Yeah, it's good to see that indexes are still king. Doesn't matter what kind of database it is. I was just working with some indexes on our vector databases the other day. So yes, and that's a great description, Ryan, because it took me a while to grasp that concept. So because it really, the manifest is the key to that, right? It kind of contains pointers to these manifest files, which in turn list the data files that belong, and that's what you're telling us gives it the scalability and all the other neat features we see with these open tables. That's pretty cool.
Mm-hmm.
Where did so that's very interesting, but where did the inspiration for that come from? Like, I think that was a very key breakthrough, working with these manifest files.
So I think it was just the framing of the problem that we knew that we needed to keep track of all the files in the table. And then from there, it was just a very natural progression. So the first thing you think is like, okay, if I don't want to go list 1,000 directories to go plan a scan, which was very, very slow, then I need to keep track of all the data files. Oh, hey, as long as I'm keeping track of all the data files, let's keep a track of the metadata about data within those files so that I can quickly scan through them and figure out which data files I don't even need to read, right? That's step one. And then you say, hey, it would be really, really expensive if I had 1 million data files and I was rewriting a manifest of 1 million data files metadata every single change I made to this table. And so you go, okay, well, hey, let's break that into multiple manifests so that I only have to rewrite a couple of files every time I make a change. And then it just sort of like snowballs from there. I think it was a very reasonable, reasonable set of decisions that led us to this architecture. It's just like it's basically Git for tables, for table data. It's very, very similar.
That's a great way of describing it. Great way, because those of us who work with data, like, the reason why this is such a big deal is at the bottom line is query performance, right? Because as you mentioned, the older formats didn't scale as well. There's performance considerations. So we're talking a little bit, I guess, about how open table formats in Apache Iceberg kind of optimizes those query performance. Can you dive a little bit more, because you mentioned indexing? Can you talk about so just in terms of query performance, in particular in the context of these large distributed data sets that you were working at Netflix and Cloudera and now at Tabular? Can you discuss the role of the file formats, partitioning, and indexing, which you just mentioned in this optimization? If you can do a little deeper, dig a little deeper on that.
Yeah. Actually, I think file formats are a good lens to understand table formats, because a lot of the concerns in file formats have analogs. So, columnar file formats became popular with Parquet and Orc, and are really game changing because they keep track of groups of rows and the metadata for each group of rows. And you can project columns from those groups, and you can also say which groups we actually need to read. And you can imagine the same problem, right? I've got some group of rows. I want to know the min-max values to know for a given filter whether I need to read that row group. Well, at the table level, let's take a whole file worth of those groups and keep track of the ranges for all those files, and sort of like get more and more less and less granular as we go up that tree. So a row group is really the lowest leaf in that tree, and then we have files that we can filter, and then metadata that we can filter, and so on all the way up. So it's really like at every level of this persistent tree structure, we want to be able to eliminate as much as we can at the next level. And that's basically how the primary index of these tables works.
And then another key architectural feature that you briefly mentioned was ACID transactions, right? Can you talk a little bit about how these open table formats maintain two of the key elements of that, which be consistency and isolation in those distributed environments?
Mm-hmm. Yeah, so what happens is I mentioned the tree structure is persistent. So we reuse as much of the tree as possible between versions. The key thing that we do here is we want just a pointer to the root of that tree. So any change that we make to the table, we basically write out the whole thing optimistically. It's optimistic concurrency. And when the whole thing is written out and we have a brand new copy of metadata, that's when you go to the metastore or the table catalog and say, hey, I want to commit this new version. And what's going to happen is you say, I'm going from the current state of whatever version, v3, and I want to commit v4. And the catalog says, yep, it's still on v3. I can commit v4. You win. And that's how it works atomically. There's just this atomic table pointer swap. Of course, if you have two concurrent writers coming in, they both say, hey, this thing is version 4. Only one of them is going to win. And then the other one's validation, hey, I'm trying to change table at v3, fails, and that writer has to retry. So that's the basis of essentially atomic commits. And then the given isolation levels are, everything is isolated because you're only ever seeing committed versions of the table, right? You can only see a properly committed version of that tree. And then you gain consistency by making checks when you run retries. So if I, start at one version and I have to retry that commit, I just have to validate that the assumptions I'm making about that prior version are still valid.
Oh, that's very interesting, right? So, because obviously some of us may be familiar with concurrency controls when doing programming. So, yeah, optimistic concurrency, that's interesting because that really speeds stuff up because you're not locking those resources. You're letting them optimistically allow the transactions to proceed independent until the commit point. That's pretty cool.
And readers don't have to do anything, which is probably one of the biggest problems with the old Hive format. Readers needed to tell everyone, hey, I'm trying to read this table, which for certain operations is just way, way, way too slow. So what ended up happening was no one participated in the locking scheme in order to get faster and faster queries. And that's where you got just unsafe behavior. So in this scheme, you can always go to the metastore, say, what's the current table state? And you get a complete, consistent, independent table state at any given time.
Great insights, Ryan. And yeah, I would encourage folks to just go look at the architecture documents for Apache Iceberg. It's a great read and an education in itself. And another feature that I think a lot of us will like, because this is a big pain point for us who are not as expert in these formats are you as Ryan, but who use data like myself every day, and that is we're always adding new fields to our tables. We're adding new tables to our databases. Essentially, the schema is changing underneath us, and even in a small team like we have, I come in the next day and like, where are my dashboards? They're broken. So I'm sure all of us have experienced that issue with broken dashboards, broken DAGs, and running jobs, and that usually goes down to the fact that the platforms we're using have this idea of the schema evolution. It doesn't have this idea. So can you tell us a bit about how do the open table format handle schema evolution?
Yeah. So this is an area where I think, I was talking about productivity and sort of the goals of the project. You mentioned something like expertise in this area. And that's one thing I want to completely do away with. I have a talk online called I don't want you to, I forget now what it's called, but essentially the talk is, I don't want you to care about table formats, right? Do you care about
Fair point
you're using in MySQL?
I don't really. They just drag me down.
Right, you shouldn't care. And that's really the reason why we wanted to attack the problem of schema evolution as well. Because we had users that would make changes to their tables and then break something. And it was because, oh, hey, yeah, if you in a SQL data warehouse, if you drop a column and add a column with the same name, that's a brand new column. In the data lake world, if you dropped a column and then added a column with the same name, you had brought back data from the dead. You had this zombie data. And all the time we would have people come from the data warehouse world, use our SQL tools, drop a column, add a column with the same name, think they're up and running, and then like leak bad data downstream. And then you've got to go clean that up. And so we just wanted to fix schema evolution and meet the, the expectation of people working with data for, I don't know, 30 years. What we were doing was not groundbreaking. It was just trying to make it so that we restored that abstraction layer so that people can work with tables as a logical container of data that has certain well-defined rules for evolving and well-defined behaviors. And just bringing us back to that level made our data engineers much more productive because they didn't have to worry about, I'm just going to get weird behavior when I add a column. Because we had one, they added a column that had been deleted 2 years ago. And then all of a sudden, the analysis of this table gave us completely bogus results because they didn't know someone had added that column and deleted it 2 years ago.
No, I love, today has been an education and some really good sound bites. Ryan, we've got Git for tables. We tend to use the phrase orphaned data, but I like zombie data much better. I'm gonna start using that. You need to do something because this is zombie data. We can't work with zombie data. That's a good way to get upper management to move. So that's pretty cool. And I got to say that the last one I want to talk about in the deep dive is one of my favorites, because back in the day when I was doing consulting for certain kinds of entities, data versioning, model versioning was always very important, but data versioning, because depending on the kind of models you were building in financial healthcare, but also data versioning. And there's been types of this around for quite a long time, but you and the community at Apache Iceberg and Open Table Format came up with this idea of time travel. So can you explain the mechanism of time travel within these table formats? And I didn't really explain my use case there because it's kind of confidential, but give us some potential applications where time travel is useful, apart from going back and betting on horse races and stock market. You want to fix?
Well, so a lot of times if you're training a model, you want to be able to have a reproducible model. So you want to be able to go back to exactly the same table state. And there are other use cases like, boring old finance. When you have audited financials, you kind of want to be able to make sure that we all agree on what the state of the table was at that time. And you don't want to lose it. You want to be able to reproduce that. And if something is off, go figure out what was wrong. A huge part of what we're doing in developer productivity and data engineering productivity is reproducible and really building trust in our data, right? That's huge, because if you don't trust the underlying system, if you don't trust the data, then that's a huge distraction to build trust and go verify, go double check, go cross-reference and do all of those tasks. So this is a super helpful feature for that reason. And it's one that we basically get for free. So I mentioned a persistent tree where every new version of the table actually points to a lot of the old data and metadata files from the previous version. And we just keep adding, tiny slices of new data and metadata or tiny changes to that tree and a new root. And that new table root identifies a new version. Well, that's how we get time travel. We just keep track of all those table roots. And actually, this is something that we have to do anyway, because we need to eventually go clean up the data files that have been deleted, and basically do that analysis of like, hey, what can I get rid of because I rewrote data and I don't want my table to just explode in size. So in Iceberg, you keep track of every single version of the table for some number of days. That allows readers that are reading that version to complete. It allows time travel. It allows incremental consumption of your table. And then if you want to keep versions any longer, you can also use, again, going back to our Git analogy, branching and tagging in the table itself. So you can tag a version and say, I want to keep this version of this table around for 2 years because that's, say, my, financial audit requirement, but I want to get rid of it after 2 years because I don't want it sitting around on disk. And so all of that is built in, alter table, create tag with the current snapshot and keep it around for 2 years. It's actually really, really cool.
No, and I love the fact that you mentioned it comes free with this format because of the way it was architected, which is a sign of very good architecture. And what's interesting as well is like some of the folks I talk to, they're becoming more aware of reproducibility. I think because of ChatGPT and LLMs, because they're non-technical folks who are using ChatGPT, and they're like asking me, why isn't your agent giving me the same response it gave 2 weeks ago? Why is it changing? Why is there not this consistency? And we know that's a problem with generative AI and stuff like that. But also, it's the same with, as you mentioned, the financial use case is an excellent use case, but many other industries as well. I expect that to be pretty much a de facto standard, because as these models get more important and how we run them, of course, you want to be able to know various snapshots in time and etc. So one interesting thing. So we just did a fairly good overview of some, but not all, the key architectural features to open table formats and Apache Iceberg. And by the way, just to our live audience, if you want to, please submit any questions you'd like me to ask. But another reason to consider something like open table formats in Apache Iceberg is, of course, cost, right? Because we can see what commute's going up. It was fine we were running these things on our local servers, local laptops, but now everything's doing everything in the cloud. And then I find once a month someone's complaining about some cost of some platform we're running. So more than ever, I see data scientists, data engineers. Well, data engineers to a certain extent, we're always cost conscious, but data scientists, AI experts, even other folks in related positions looking at cost optimization, because data lakes and data warehouses can get pretty expensive. Can you, I know you've already kind of covered this in the architectural overview, but can you talk a little bit more of, but I do believe it's an optimization part of it as well. Can you talk a little bit more about why the more traditional formats are so expensive, and why data warehouses and data lakes are so expensive to manage from the context of this interview? I know there's other reasons, but from the context of what we're talking about here.
I would say this is a really complex subject. So I'll give a couple of responses, but I would say don't by any means consider this comprehensive. So I think one of the concerns that I'm excited about sort of changing in the data landscape is the incentive structure for making your data better. Like right now, you're the only one with the incentive to make your data better. Because like if you're paying to store it and you're paying to compute on it, then like the only thing that a given vendor cares about is that you're happy, right? And not that you're paying them less. Like paying them less is not a goal. You being happy is a goal. And so like even though those things are closely aligned, it's a proxy measure. And I think that separating data into a more centralized solution allows you to have a vendor that you pay to make your data smaller, make your data better. Like that is not fighting with another part of the business because, hey, like that's a revenue line item. right? And so I think that separation of compute and storage at a vendor level aligns incentives in a much better way. I think also just like the business model of database vendors for the last 30 years has necessarily been get all the data in our database and then help you use it, right? And now that that's changing, now that we have the ability to like share high quality and data sets with SQL behavior across systems, like that sort of model just changes to where you want to store all of your data in as cheap a system as possible. So just like throw everything in S3 and then bring vendors or compute solutions, specialized compute to your data. And I think that really changes it, because you can just throw everything in S3 and not have not pay the price of being able to license a proprietary storage stack, right? A proprietary storage stack is going to be incredibly valuable to make that compute system effective, because the storage stack, it provides opportunities for the query layer to do smart things, read less data. And so if you're putting your data in a proprietary system, you're paying for something that is incredibly well designed. But now you've got an open format that is well designed and has those storage opportunities as well. And so, is it worth that premium anymore? So yeah, I think we're going to see a world where the alignment is much better. You're not paying a premium for proprietary storage that is, very, very good, but expensive. And then on the Hadoop side of the world, I would say the inability for us to actually maintain and change data sets, because it wasn't safe to make those changes. We didn't have ACID transactions or atomic operations at all. It caused us to just not maintain table data. I can't tell you how many customers I talk to that are like, oh yeah, we've got like, millions of 2 megabyte S3 objects storing our data. And we're going, whoa, you can save so much money by compacting and clustering and like maintaining your table data. We're seeing like 30 to 60% size reductions just by having services that automatically maintain your data. So on the Hadoop side, I think the opportunity is even bigger. And that's all automated now, which is awesome. By the way, I'm totally biased here. That's what my company Tabular does. We automate all of that table maintenance and headache. But like I think there's a massive opportunity to make databases in the analytics space simply cheaper.
Ryan, yeah, as you said, that's definitely a complicated subject, but I think you've definitely shared with us some really good things to think about and great insights. I do want to go to one user question. Let me see here. Let me show this question and just read it out for our podcast audience later. So would Apache Iceberg, through its metadata management and tracking patterns, CDC, solely have a role in shaping data governance and eventually feature engineering / labeling data sets? And CDC here, for those of us not familiar with, that's change data capture. If you want to tackle that one, Ryan.
Oh, this is big. There's a lot here. So Iceberg certainly has a lot to do with enabling new CDC patterns. I actually have a blog series on tabular.io/blog about designing CDC systems, which is basically the design that we use for our CDC service internally. So like I would recommend people check that out. I think that's too large of a subject to go into. Feature engineering and labeling, I think we Iceberg pretty much is a data format for those sorts of tasks. So I don't think it changes too much there. And the main one I want to tackle here is governance. And I know we're probably going to get into this later, but the big thing that Iceberg does as an open table format is it allows you to share storage underneath multiple compute, like specialized compute offerings, compute engines or query engines. And that changes governance dramatically, because now we have to think about how to govern and secure data in a world where there's not just one way in and out. There are lots of specialized compute engines that all need access to the same data. So how you govern and manage access controls is just changing in the marketplace. And I think in 5 years, we're going to have very tight access controls at the data layer rather than at the compute layer where it's traditionally been.
Well said, Ryan. Yeah, and just pulling that thread from that question, talking about featured and labeled data sets. Can you tell us how open table formats can be used to streamline data access and management, in particular for machine learning and data science workflows?
Yeah. So I think the biggest contribution of open table formats for machine learning is that the scalability factor. So imagine you want to run a machine learning workload on a traditional data warehouse. Well, a traditional data warehouse, there's one way in and one way out, and that's through SQL, right? And that's great. That is absolutely great for analytic workloads. For machine learning, though, I might want to have 1,000 Metaflow Python processes all spin up at the same time, and all go read the same data set and the same portion of the data set with different tuning parameters, run and build a model, and output their results. This is like the thundering herd problem, which is you've got so many people accessing the data at the same time. If you've got a extra large warehouse sitting there, you can't have 1,000 Python processes all spin up at the same time, all grab the same data set, and not completely overwhelm that system. What you can do is have them go directly to S3 for the data files. And so that's what open formats allow you to do. These 1,000 Python processes all training a model with different tuning parameters, they don't need the database to scale to that level. They don't need you to spin up a whole bunch of new warehouses and do something there. They just need to be able to all access the same data in S3. And so it really provides this scalability that you can't get anywhere else. And it's the same mechanism that allows Spark and your data warehouse and Trino and Flink to all use the same table at the same time, right? It's that all they're sharing is this reference to the table from the metastore. Hey, give me the latest metadata from the metastore. I can plan a query. I can go figure out which data files I need to read and go read them directly from S3 because S3 scales globally.
Fascinating. That's really, really good information. And I would love to spend more time getting into AI and machine learning, but there's a few other questions we want to get to because I know we're moving along here and time is eating away. So we talked about the cost aspect of this, but a little more on the title suggests like disruption end of it. Can you elaborate on how open table formats are reshaping the data industry? You mentioned a bunch of tools there, and are they replacing existing tools, or is it more of a collaborative evolution?
I would say open data formats are surprisingly combining or bringing the two halves of our data landscape back together. So in the Hadoop and data lake side of things, we had multiple tools, and our task was to upgrade our data lake to have the reliability, performance, and guarantees of a data warehouse. The data warehouse already had all those guarantees, but like I said, you had one way in and one way out. And the open table formats, what we did was we made it possible for all of those tools to safely and reliably with SQL warehouse behavior to work with one another. And that was actually a really big thing. We set out to solve atomicity and have ACID transactions in Spark that did not affect readers in Trino. But what we actually did was we built a system in which you could have truly shared storage. You can share the data sets underneath those two things successfully, no matter who's modifying them. And that's attractive to the data warehouse world because they want access to all the data lake data. And so people have been, sort of building open formats into everything these days. And the end result is that you're going to be able to have a single data warehouse, right? Data warehouses where the idea is bring all the data together. But you still had multiple data warehouses, or your data warehouse was too expensive, so you kept some data just in S3. And now you can have truly one system where all your data is stored with the cost profile of an S3 and have all of these specialized compute services come access it. That's groundbreaking. We've never been able to do that in analytic databases. And the world is changing based on that centralization of data. When data becomes centralized, what happens? Well, it changes the cost profile, like we were saying. It increases the number of things that you can use with that data. But to the earlier point, it also means we need to move access controls and governance down to that data layer. We need to make the data layer more capable, add those indexing and table maintenance features and things like that.
No, that's spot on because for I don't think we mentioned this in the architecture side of it, but Apache Iceberg was built with cloud-based services. It was built with support for separation of compute and storage, right? So on the compute side, I know it's working with Spark, Think, Trino, as you mentioned, Dremio. I think it even has integrations to Hive as well. So it definitely sounds like it's more like collaboration.
Mm-hmm. Yeah, I mean, it's very collaborative, but I think it's the main theme that I keep coming back to is data architecture is changing in what becomes centralized and what remains specialized. So data sets themselves are going to be centralized. Governance, I think, is going to be centralized. Then you're going to be able to plug in batch and ETL compute, machine learning compute, data warehouse compute, streaming compute, all of those things on top. Those are specialized components that all interact with this centralized common data plane.
Yeah, that makes a ton of sense. And Ryan, you mentioned earlier that you were working with some companies and looking at their data and how to architecture and how to structure it. That's going to be very interesting because, let's say I'm an organization. This all sounds great. I want to transition to open table formats. What's the primary advice you're giving these organizations? Because we all know, moving, especially people get very, very flustered when you start talking about moving their data into a different architecture or structure. So what's advice do you give to for a successful implementation to these data engineering teams, these organizations?
Well, yeah, hopefully this is one of the last moves, or we're not going to have as many moves, because you shouldn't need to move data to use different compute anymore. That's huge, right? That is, I think, one of the most exciting outcomes. As far as how to adopt and what advice I give people, first of all, I want people thinking about this world in which data is centralized and compute is specialized. So think carefully about what components you're putting where and how those things connect to one another. This is where we get into sort of how we are taking the Iceberg community forward to make this generally easier. But I think you want to aim for that centralized data layer that can connect to any compute that you want to use. So that should be your general mindset or goal. The practical side is that you need that connectivity. And you also want to view this as not a simple drop-in replacement for your Hive tables. Hive is a very simple system that didn't allow us to build services and maintain data. So you couldn't automatically optimize your tables. At the same time, it didn't require maintenance because there was no maintenance that we could do. Iceberg both requires maintenance and gives you the ability to maintain and optimize your data sets. So the required maintenance is, like we talked about, we have this history of every single version of your table for some number of days. Well, something needs to go and garbage collect the tail of that, so you're not spending money to store data for all time. And so like the nature of these modern table formats and open table formats is that they require some amount of maintenance. So just keep in mind that you're going to need to solve additional problems. And then, you know, there's both additional problems you have to solve and then additional opportunities that you want to solve. So you have to solve things like keeping the table clean, deleting old data files, garbage collection, like that sort of thing. And then the opportunities are huge. Like I was saying earlier, that cost vector, bringing down the cost of your data by actually maintaining it. And by the way, if your data shrinks by 50%, your compute costs usually shrink by 50% too. So like there's a massive opportunity there. There are open source ways to do those things, right? If you have a Spark cluster, we have stored procedures that's like, hey, go expire snapshots in this table and delete stuff. Go compact this data set over here. But there are also commercial solutions. Tabular is one of them, where all of that stuff happens automatically for you. So it's really about knowing that those problems and opportunities exist and having a plan for how you're going to manage them.
Definitely very good advice there and insights, Ryan. And I'm sure, as people can say, if they reach out to you or Tabular, they'd be in very good hands, because this is an area where lots of companies I know are struggling. So just want to wrap up in the last few questions here. What's next for open table formats and Apache Iceberg? What's on the horizon roadmap, so to speak?
I'm really excited. So I'm really excited about this centralization of data and what changes. That goes beyond a table format. Apache Iceberg was really good at saying, like, here's how we're going to agree on what files mean and what files are in a table and have the ability to sort of work with data cleanly. I was on that Schema Evolution soapbox for a very long time. But now that we're thinking about centralizing data and what the broader implications of shared storage are, we need more things. So this is really where the Iceberg community has been going for the last few years. So we need a common catalog protocol, right? How do we talk to the catalog that does that commit operation? What are the capabilities of doing that? And most importantly, how do I make sure that everyone talks the same language? So in the past couple of years, the community has introduced the REST catalog protocol, which is a common way for all of the engines to talk and interact with a catalog. That's critically important because in the early days of Iceberg, you could plug in your own catalog. You could write your own. We had a Java interface for doing it. But as we go and broaden the community to multiple languages, we have Python, we have Rust, we have Go, we've got the Java implementation. Well, we don't want to have to provide an implementation of your catalog to every language. And you're never going to get that into, say, Redshift, right? So it's important at this point that we agree on how to standardize that protocol and how to interact. Then there are follow-on things. How does that protocol, that catalog interaction, or how does that relate to access controls? And that is incredibly important, right? Your catalog, if we're moving access controls to the data layer, your catalog actually needs to be involved. So we also have standards for catalogs to be able to delegate access to the engine that's coming in, and using OAuth so that you can authorize those engines, things like that. We're also working on views. So the Iceberg 1.5 release, which I want to highlight, just came out, has initial view support in Spark, and we're working on getting that into Trino. And that is cross-engine views. Because again, if we're centralizing this layer, we can't just have tables. We need also views and some of the things that really are core pieces of data engineering in practice. So we're working on that. We're working on encryption. We're working on better statistics for query planning through the use of metadata sketches and things like that. So there's just a lot of work to do.
Yeah, to say the least, that's quite the list. I'm getting excited about hearing the excitement in your voice about all the stuff that's going on. Wow, that's a fantastic list. And I kind of regret I didn't ask that question halfway through, because there's a ton there I would love to ask, but unfortunately we are running a little short in time here. And Ryan, you're speaking virtually at our Data Engineering Summit, which is co-located at ODSC East in April, and your session will be at best practices for CDC pipelines to Apache Iceberg tables.
Mm-hmm.
Again, that's CDC pipelines. That's change data capture, not the Center for Disease Control. For those of you who just know. Can you talk a little bit about your virtual session? I'm pretty sure you can join for free as well. Go ahead.
So I think that we worked with a partner to basically develop real world patterns for CDC. And this was to solve multiple challenges. We think of CDC and open table formats as just dump the data in and you can represent it and it sort of works. The problem is there are a lot of complex things that you need to keep in mind, right? Do you want to be able to replay those changes that were going into creating your mirror table? Do you need transactional consistency or eventual consistency? So we developed a set of, I think, best practices and patterns for transactionally consistent mirroring, which means basically, if I had a transaction operate in my original transactional database, and say I created 2 rows in different tables at the same time, when I see that data in my analytics system, I need those 2 rows to both exist at the same time, right? I don't want to have a state in my analytic mirror that is inconsistent with the state in my upstream, because that eventual consistency introduces a whole lot of what I call in the blog post data gremlins. They're extremely hard to track down problems because you're violating a data engineer or a user's assumptions about consistency between tables or between rows in that table. And that's very, very hard to track down. So a CDC pipeline that delivers on the expectations of those data engineers and consumers of that table.
Yeah, Ryan, this is so good. We've learned so much over the last hour or so. This is definitely a podcast where I'm going to take some time this weekend and probably in following weeks go back and listen to it, because everything you've been telling us, I really think has been spot on and very sound advice, even for those of us who are tangential to the data space. So very, very informative, I must say.
Thanks.
And how can people best follow your work or get in touch with you?
I would say follow Tabular on LinkedIn. Every time I do a podcast or give a conference talk or something like that, we're going to post links there. Also, my blog posts and new writing and things show up there, as well as I think some pretty valuable tools. I think Tabular is basically the system that we wanted to build at Netflix. And so I'm pretty excited about what we're building there, and excited to share that too.
Yeah, and I was just looking at the blog sites. They're fairly prolific, which is excellent. Lots of great insights on the Tabular blog site. So I would encourage people to follow, as you said, follow Ryan on LinkedIn. Definitely check out the website. I'm just looking for a subscription here or something where I can get them in my inbox. But this looks really good. Ryan, once again, thank you for being a great sport and coming in the podcast, sharing so many valuable insights. Thanks for being a speaker at ODSC. And look, that laundry list of features you had around Apache Iceberg and open table formats, we definitely want to get you back in 6 months or 12 months and tell us all the new stuff you've rolled out. And yeah, keep doing the fantastic work between you and the open source community. This is a great project, a great resource for the open source community. I would encourage people to look at the documentation, look at the architecture, see if this is something you want to adopt in your community, because it's in your organization, because it's pretty special. So Ryan, thank you again so much for all your work and contributions to the open source community.
Thanks for hosting me. It was a lot of fun.
Wonderful, and we'll chat again. Okay, everyone, that's a wrap for this week. Thank you for being a great audience. Don't forget to check out our podcast page on odsc.com/podcast. Don't forget to check out ODSC East and our Data Engineering Summit and some of the other free webinars we have going on. Otherwise, we'll see you at the next one. Thank you and bye for now.